Okay, let's talk about the Alaskan moose. In number 7, there is not one Alaskan moose, but two um, Alaskan, and here's where we have to decide, is it mooses, meese, moosin, or just moose? I think it's probably moose. I may use any of these. Okay, so there are two meese, and they are running towards each other, and they collide inelastically. Okay, a word that is missing from this problem that should be in it is perfectly inelastic. So these two meese are going to run into each other, collide, and get stuck. Um, so we're going to use the conservation of momentum to figure out what happens at the end. Not only what will their final velocity be as they move together, but it wants to know how much kinetic energy is going to be lost as a result of this collision. So I'm going to just go over here in red real quick and write the initial kinetic energy. Okay, how much kinetic energy is there initially? Well, it's 1/2 times the mass of a moose times its velocity squared plus 1/2 times the mass of a moose, and I'm just writing m because they're both 800 kilograms, times its velocity squared. And when I plug in numbers, what you'll notice is that it doesn't matter what direction they're running, their kinetic energy is going to be positive. Oops. So this negative is kind of unnecessary. When you square it, it's going to become positive. But it is necessary for the second part of the equation when we talk about momentum, because momentum is a vector, meaning it has direction. So at pre-collision, there are 40,000. Do you remember the units for kinetic energy? That's right, it is joules. There are 40,000 joules of kinetic energy before the collision. And so now we'll come over here and we're going to deal with the collision and find out how fast they will be moving together afterward. Okay, so we've got the mass of a moose times the initial velocity plus the mass of a moose times its final, or its initial velocity, which is negative. Okay, so this is really important. One of them is moving one direction, one is moving the other, so one has to be positive, one's negative. I decided that the first moose is the positive speed, or the positive direction, so anything going right is going to be positive. So when I find the final velocity of the moosin, if it's positive, that means they're going together to the right, which is what I am predicting is going to happen. So at the end, we have the mass of a moose times the final velocity of moose 1 plus the mass of a moose times the final velocity of moose 2. And there's multiple ways you can go about this. You can plug in 800 for all of the masses, but here's the thing. Every single term has the mass of a moose in it, which means we can divide by the mass of the moose, and they all go away. So on the right or the left side here, we've got 2. On the right side, we have the final velocity of moose 1 plus the final velocity of moose 2. Well, those final velocities are the same. Final velocity of moose 1 equals the final velocity of moose 2. So we've got final velocity plus final velocity. What that? 2 final velocities equals 2. We divide by 2, and we get that the final velocity of the mooses is 1 meter per second. But that's not even what the question asks us, but it is critical in us finding the answer to the question they ask us. They asked us about the final kinetic energy. How does it compare to the initial kinetic energy? And this is a way of determining, in a way, if one of these things, if the collision is elastic or inelastic. If the kinetic energy at the end is the same as it was at the beginning, it's an elastic collision. If it's different, then it's inelastic, even if it's not perfectly inelastic. All right, so I just wrote one term here, because I could put 1/2 times 800 times 1 squared plus 1/2 times 800 times 1 squared. But let's do 1/2. The total mass of both of those moose is 1600, 800 plus 800, and they're going 1 meter per second squared. And so that is a final velocity of 800 joules, a final kinetic energy of 800 joules. So how much did the kinetic energy change? Well, that's just kinetic energy final minus kinetic energy initial. And the difference is negative 39,200 joules of kinetic energy. I think there are 2 significant digits in this one, yeah? So that would be negative 39 kilojoules. Kilo meaning 1,000. So that's how much kinetic energy was lost. But notice the amazing thing, that momentum is still conserved. And so we love momentum because it's always conserved. So we can always use this equation and figure things out using this knowledge that momentum is always conserved. So that's number 7.